So in this lecture, we will discuss about the L2 regularization. So first, we define what is L2 regularizations and how it is useful to overtake the overfitting and underfitting problem. Okay, so let's start. So first, we revisit our previous lectures. So what we get from our previous lectures? We get that our optimal W, that is we called it as W star, is equals to arc mean of over W when our I is 1 from 1 to n, means n is actually the number of training data points, 1 plus exponential of minus yi W transpose xi. Okay, this you got it as our mathematical optimal problem. Okay, mathematical optimization problem. This is problem. Okay, first, for easy of our writing, we just call this term, that is our sign distance, we called it as a time. So first let our signed distance, we call it at zi. Zi is what? Yi W transpose xi. This is we called it at zi. In sign distance is called it at zi. So what will be our term then? Then our term is, after applying the zi, then our term will be minimum of W I is equals to 1 to n log of 1 plus exponential of what? Minus zi. That is our signed distance. Okay. So first, let's consider this function. What is the behavior of this function? This term. Let's change the color. What is the behavior of this function? Means first we see the our function. Just for easy of time, just recall what is minus of e to the power minus x. Just see the graph first. If we see our graph, okay, this is our graph. So if you see the in negative axis, this function is decreasing. This is actually monotonic first. First we observe that. Suppose we call this term as our zi, and this axis, that is our dependent axis, is equals to our exponential of minus zi. Okay, if you just see it, this function is a monotonic function. When we increase the value of zi, then the function is reduced. That is monotonic, means actually this is a monotonical decreasing function. Okay, so first write down this. So just a minute. Okay, this is a monotonically decreasing function. Monotonically so main function is equals to our e to the power minus x. This is a monotonically decreasing function. Okay. And one thing you will notice, if we maximum z value, if our zi is tends to infinity, then what will be the value of our functional? That is exp of minus z, and what? Then this tends to 0. As you see here, just see from this picture, as our zi increases, and as it increases, just zoom out this picture, as our zi increases, then this functional value goes to infinity. Just see it. when our x is equals to the see the parameter value x value when as t is equals to tends to 50, then it's so small, so small. Okay, so from this we got this limited limit that is a limit concept. Okay, just go back to the okay, this is the behavior of this. So our functions is now just read down, write down the function. Our what is our function? Our function is 1 summations of I is equals to 1 to n log of 1 plus exponential of minus zi. And what is the value of zi? You see, zi is always greater than 0. This function, this value, this functional value is always greater than 0. Okay, just see the graph, then you can see. Just see the graph. This value, this value, just see the graph. This value is always greater than 0. Okay, in every domain of this region, this value is always greater than 0. Okay, if this value is always greater than 0, then what? And we know, and we know that, we know what we know. First, log of 1 is what? Log of 1 is 0. And if log, and we know log is a monotonically increasing functions. Okay, for this we can write log of 2 is always greater than log of 1. And what? And again, if we write, it's small changes, one to small changes, all plus delta is always greater than is equals to log of 1, and when delta is our greater than equals to 0. Using these monotonically functions, monotonical conditions actually. Since log is a monotonically increasing function, just use this for monotonically concept here. Just we apply this concept here. Since this function, since exp of minus zi greater than is equals to 0, then what? Then the total functional value will be greater than is equals to 0. Since log 1 is equals to 0 and this equals to from this formula. Okay, we call it as this functional value is greater than is equals to 0. Okay, now actually what is our W star? W star is equals to arc mean of W summation I is equals to 1 to n, that is number of data points in our training data sets, log of 1 plus ex, that is exponential of minus zi. Okay, this will be what? This will be from previous step. This will be greater than equals to 0. Just wait from here. So, and we find the minimum value. So, what will be the minimum? All the value, all the summation value is greater than 0. Greater than all this summation, greater than equals to 0. So, what will be a minimum? It is clear. It is very clear that our minimum value of this function will be 0. So, the minimum value. So, the minimal value of this I is equals to 1 to infinity log of 1 plus exponential of minus zi is what? Is 0. Okay. And one thing is what? One thing is that if our z means is what? Z means is if, just write down it. Just write down this. If zi is positive, and zi tends to infinity. Then what? If our zeta is positive and zeta infinity means this is plus infinity. Okay, zeta is positive and zeta tends to infinity means what? Zeta is plus infinity. Then our exponential of minus zeta tends to 0. Just see it from our picture. Then from here we can conclude that log of 1 plus exponentials of minus zi is tends to 0. It occurs when? When it occurs, the main thing. It occurs when our all the zi value, not only single zi. Z is what? Z actually zi is what? Zi is yi. That is signed distance actually. W transpose xi. And this will occur, it will occur, just write it. Okay. Just change the color. And just we take another color. It will occur when it will occur? It will occur when our zi tends to infinity. Means for plus infinity for all I. This symbol is called the for all. For all I. This function will be taking the minimum value when our zi tends to plus infinity for all I, for si. Okay. Just rewrite this question. Now our zi is yi w transpose xi, and we already know xi and yi and xi, we have already know this. This is what? This is our data set, training data set. Okay, and this will contains our xi, yi. I is from 1 to n. This is our training data set. Okay, this is our training data set and this is our zi. Okay, if the total term if the total term is positive, then what happen? Means if total sign distance is positive, means our set is correctly classified. Okay, we learn it from our first lecture. Okay, just remember it. If our sign distance is positive, then our class is correctly classified. Correctly classified. Okay, and we have already known this set. So our and we in that find that we just recalculate that our zi tends to plus infinity, then we got the minimum value of our optimal problem, that is 0 when zeta is plus infinity. So to modify it, and we already know our from zeta that our xi and y is coming from our training data set. Just one thing is variable here, that is w. So for this we just we have to modify w in such a way that h zi tends to plus infinity. So we just matter here w. We have to modify w here. We have to modify my w. modify it in such a way, in such a way, okay, that our age zi, that our age zi tends to positive plus infinity. Okay, so what? So first we can, if we conclude this thing, we have arrived. First one, if zi, if zi is equals to our positive, if zi is equals to positive, then what? Then xi is correctly classified by w. If zi is positive, then xi is correctly classified. Xi is correctly classified by w. Okay. If our xi zi is positive, then xi is what? Xi is correctly classified by our taking w. Number two, what we have seen, and zi tends to plus infinity. Then when zi tends to plus infinity, then we only take our minimum problem, that is the minimum value we have to find. Actually, at the end of the day, we have to calculate this value. This is our the optimal problem. Okay, when we got it, when we find this minimum value, when first z1 is plus infinity and z1 is also positive. Okay, just read it. Z is positive means what? This means that the xi is correctly classified and zi is plus infinity. Okay, if I pick, means if I pick my w in such a way that z is positive, means xi is correctly classified by w and zi is plus infinity. But one thing, you see that zeta is totally dependent on w, means xi and yi is coming from our training dataset, that is our fixed. We don't know about this term. Okay, only we have to handle the w. If our zi tends to plus infinity, then what will be the value of w? Then what will be value? Then w I is also plus infinity, then wi is also plus infinity. Okay, just right. But we have some problem about this. What is the problem? We have some problem of here. Just if we see the problem, then our problem is what? Then our problem is outlier problem. Number one is our problem. If first problem is our outlier problem, this second problem is misclassified point. Okay, zeta if positive, then we will have already know the xi is correctly classified. But we have two problems. So one problem is our outlier problem. Second problem is our misclassified problem. Misclassification problem. Now we have to tackle these two problems. Okay, we have to handle. This is the main task. We have to handle these two problems. We have to handle these two problems. Then everything is okay. So how? Now main matter is that how we have to handle these two problems. Okay. So first problem is the overfitting problem. Overfitting problem means what? First is our overfitting. Okay, means what? Overfitting means what? Overfitting means our model doing job perfectly. Okay, means our model, we have that we build our model, it is performed 100% accurately. Okay, small changes in my data set, it will change dramatically. drastically. Okay, this is called our overfitting problem, or simply it will called our high variance problem. Means it will done perfect job. It will done our perfect job on our training data set. Okay, this is the problem. Number two is what? Number two, as we see, just write down it. Wi is plus infinitive or Wi will be minus infinitive. Then only that we will come on to our optimal problem. If you see the graph, if you see the graph, then when it will find our means exponential, how do we find our minimal value? That is when zi tends to plus infinity. Okay, and when zi it will be tends to plus infinity, it will be actually going arises plus infinity when W transpose. Actually, W is what? W is nothing. W is a vector, set of vectors which have some components. Okay, this block diagram of W, that is W1, W2, W3, similarly WD. WD is such a vector of a d-dimensional. Okay, as we from previously we called it as d-dimensional. Okay, just assume W is a d-dimensional vector, and it will when it's depend W final W is depend on its component. If one component is infinity, then W net may not be fulfilled plus infinity. If it is S component, if its S component is infinity, then only W will come to plus infinity. Okay, and or otherwise we can say W, if W is component of W is minus infinity, then it will be happen that our W is minus infinity. So finally it is totally depend on its S component. Now let's write down our regularization. So this is the problem. First, if we taken such kind of things, then our model is totally overfitting, and it will just on our training data set, it will doing a perfect job. But if we change the small data on our training data set, then we dramatically change. So we faced here a high variance problem. Okay, and one thing is that our W is nothing. W at the final day, W is perpendicular to our plane. If W is plus infinity or minus infinity, then we have to tackle some problem. Just see it. Just see the what kind of problem. If W is plus infinity and minus infinity or minus infinity, then what kind of problem we have to face to just see it. So first write down the what is the regularization. Now L2 regularization. Regularization. Okay, so we use this regularization for what? For tackle where between overfitting and underfitting. To tackle the overfitting versus underfitting. Okay, one thing, overfitting means what? Overfitting means our high variance problem, and underfitting means what? Underfitting means high bias problem. Sorry. Okay. So to one thing we have to remember first, just write down the just remember it. If wi is all the wi is, okay, all the wi is plus infinity, or all the wi is tends to minus infinity, then only we our mathematical optimal problem reaches the minimum value. Then our minimum value only arises then. Okay. Now one key aspects we till now we have not used here in our mathematical optimum problem. That key aspect we have to use here. So we know W is what? W is our normal vector. W is what? If it is our decision surface, if this is our decision surface that we call it as pi, then W is nothing. This is a perpendicular to our plane. So if since W is a normal vector to our plane, optimal plane is a normal vector. So we call it W transpose plus W is equals to 1. We know it from our mathematics. If anything is normal, then its transpose multiplication with its transpose value is will be always 1. Okay, just use these concepts to build our regularizations. Okay, and why we called it as L2 regularization. Okay, this is the main thing. So our main regularization will be to avoid our overfitting and underfitting. We used here our regularization term. So just write down what will be our regularization term. W star is equals to arc mean of W, then our summed value of the signed distance, log of 1 plus exponential of minus yi W transpose xi, that is our signed distance, plus lambda W transpose W. Okay, this is the, just don't be confused. Now what is lambda? We will discuss it. What is the lambda? Okay, just think about this term. Now here just think about this term. Okay, actually this is what? This is 1, since W is our normal to our plane, so W transpose W is 1. So if W transpose W is 1, and we know W transpose multiplications will be, so W transpose W, the multiplications will be summed of I is equals to 1 to what? W is equal to D dimensional Di. W, so just write down here G, W, G. Okay, we already know it. The summed distance, the multiplication W transpose W is written as like this. Okay, so this term will be now written as lambda of summation I is equals to 1 to D sorry J square. Really, we have to multiply such a way that and empirically we written as this will be as one of our top. This for for this, actually this is a L2 norm. Since we using this multiplications and it is L2 norm, so we call this regularizer as L2 regularizer. Okay, because of this, only because of this L2 norm, only because of L2 norm we called it here L2 norm regularizer. Okay, so this term here this term we called this term is a loss term, and this term we call is as regularizer term. Okay, this term is we called it as loss term, and this term we called it as regularizer term in our problem. And at the final day we have to minimize this to find our best W. Okay, when, and one thing we have see that when our Wi is tends plus infinity or Wi tends to minus infinity, then our loss term is what? Then our loss term tends to 0, and regularizer term, actually it is finally it is don't matter if positive or negative. If we taking the norm, then everything will be converted to positive. So at the end of the day it will coming very large, since Wi tends to plus infinity or minus infinity, so our loss term increases. Okay, just see it, our loss term, if we taken our W as large, okay, our loss term is decreased taking our minimum value, but our regularization taking the very large value, very large value. So we have to handle this wire between this regularizer term and regularizer term and loss term. We have to handle the situations between these. Actually they are very wire between loss term and regularizer term, they are a wire. Okay, we have to handle this thing. Okay, when z equals 2 plus infinity means this. Okay, now we have coming to the picture our hyperparameter. Okay, just see it that when we taken the our W is plus infinity or minus infinity, then our loss term will tends to 0 and our regularization term will be very large. Okay, then our just come into the picture our regularizer term. Now our regularizer term, that is lambda, come in the picture. That is our hyperparameter. We call it as hyperparameter in logistic regression. In this lambda is called the hyperparameter in logistic regressions. Now the main thing is that we have to handle the lambda value such a way we have find our best solutions. Okay, we have to find out. Just see it in KNN. In KNN, what is our hyperparameter? Our hyperparameter is K. Let's say hyperparameter. In KNN, we see that in KNN, our hyperparameter is K. In Laplace smoothing, when we apply the Laplace smoothing in neighbor base equation, then what will be our hyperparameter? This hyperparameter is the alpha. In neighbor based, our hyperparameter Laplace smoothing is alpha, and this is called our. And how to find our best alpha? So in using cross validation, we using our best alpha. What will be our best alpha? Okay. So here, if we taking lambda is equals to 0 in logistic regressions, if we taking lambda is equals to 0, then what we will find? Then we will find that if lambda is equals to 0, then our regularization term will be totally 0. Then only rest of the things is our loss term. Then what happen? Then if regularization term is 0, then we have facing the problem is overfitting. Okay. That's in trading data, our model work perfectly if our loss term is 0. Overfitting to the training data set. And what if lambda is equals to very large? If lambda is equals to very large, then what will face? If lambda is equals to very large, then we faced that this term is 0. And if w is plus infinity, then loss term is 0. Then what is the rest of the thing? This is the very large means lambda is very large means regularization term will be very large. Then our data set, we have no role. Actually, this term facing the going to 0 tends to 0. Actually, our data set, our applications on the data set, no effect, has no effect on the final w star. Okay, and the only rest of the thing is our regularizer term. So in such situations, we have faced the underfitting problem because they have any no role on our data set. So we have faced here underfitting problem. Okay, underfitting problem we have faced here. So the end of the day, we have find that minimum of loss functions over training data, loss functions over training data plus what? Plus we got our regularizer term. Okay. At the end of the day, we have to minimize these two terms. Actually, loss functions term on the training data and our regularizer term. And we have seen that, and we also see that if our lambda is equals to 0, then we got our model is totally overfitting model. Overfitting model means what? Means high variance problem. We have faced a high variance problem. We have faced a high variance problem. If lambda is very large, then what? Then this is a very large. Then what? Then this is our underfitting problem. Then our model is underfitting. Okay, if lambda is 0, then overfitting. That is, we faced here a high variance problem. If lambda is very large, then we have faced the underfitting problem. Then what will happen here? Then we faced here a high bias problem. Then we faced here a high bias problem. Now the main thing is that we have to find that lambda. We have to find the lambda in such a way that our model is not overfitting as well, and also it is not a underfitting model as well. So how to find it? As similarly neighbor based equation model or k neighbor model, we have to finding by using cross validation. we have to find it. We have find the best lambda by using cross validation. By using cross validations. Okay. Okay. I think this is clear. Till now we have discussed. First, just remind what we have learned from this lecture. So we have learned using our one regularizer term, that is we called as a real to regularizer term, to tackle the wire between overfitting and underfitting. So how to? We first see from the graph, the minimum problem occurs when our z, that is our signed distance, is plus infinity, and when our signed distance is plus infinity, when our wi, that is the component of the weight vectors, is plus infinity or minus infinity, only then it is possible our zi is plus infinity. And since our xi and yi in our signed distance is coming from our training data sets, now we have only tackle with w, nothing else we have to handle, because data sets is totally, we have no handle our data, it is totally independent, just we have handled w, that is our weight vector. So we have to modify our w in such a way that zeta tends to plus infinity. And here we have faced two problems. One problem is outlier and misclassification problem. And we are, from our lecture one, we have already know that if our zi, that is our sign distance, is positive, then our xi is correctly classified by our w. Okay, and zeta is plus infinity, then we have see that if zeta is plus infinity, then the probability chance, from the probability we see that the probability chance to be the class plus 1, okay, it is tends to 1, the probability tends to 1 when zeta tends to plus infinity. And so here we have faced that we have faced our overfitting problem. Overfitting for what? Actually our this model is doing the perfect job on our data sets. Means what? Means if we small changes to our data, training data, then our model it changes dramatically. This will lead to so bad situations. Okay, so to avoid these situations, we have used the regularization to tackle between overfitting and underfitting. So how we will avoid? Because in our equations we know that from our equations the w is a normal vector, and in normal vector in mathematics we know that w transpose w is equals to 1. Just use this concept here in our optimal problem. So in our optimal problem we used lambda w transpose w. So this term, that is our locked ops exponential, that is our summation I is equals to 1 to n log of 1 plus exponential minus yi w transpose xi, this is called our loss term. And another we have tackled the regularization term, that is lambda of w transpose w, and lambda is here our hyperparameter. We have to find the best lambda to tackle this. And the loss term and regularization, here we have the where between these two terms. Okay, as you see here, we have called the L2 normalization, because here we have using the L2 norm of our weight vector. So we called it as L2 regularization term. So first we see that if wi is all the wi tends to plus infinity or minus infinity, then our loss term is very tends to 0, and our this term regularization term is going to very large. Okay, in such situations we have find that this is our a overfitting problem, overfit model. So to find this, we see that if we our hyperparameter we taking as 0, then we find this is a overfitting problem. Simply here we have not used any regularization term. This here we faced that this model is a already overfit model. And if we take our lambda is very large, then it is an underfitting problem, because of lambda is very large, we have just avoided our avoided our loss terms. Avoided loss terms means what? Avoided loss terms, we have don't care about our training data sets. If we don't care about our training data sets, then what we have faced? We have faced this problem is underfitting problem. Okay, so at the end of the day, we have to calculate this term, loss function term and the regularization term. So we have facing underfitting problem. Now we have to choose lambda in such a way that we have to find not our model is not mass overfit model and is not mass underfit model, and thus this is balanced between two. Okay, so how we choose it? As previously from neighbor based or KNN, we choose it as using cross validations. Here we have also using the cross validation to find the best lambda, and it will be see in the next lecture. Okay, thank you.